Good morning, students. In the last video, we were not able to write down the theory part of second law of motion due to some technical problem. So we'll just write it down in this video in the starting part with along with its statement. The statement suggests the time rate of change in momentum is directly proportional to the resultant external force, and the change in momentum is in the direction of resultant external force. Now we'll derive its formula, that is F equal to ma. Suppose initial velocity of an object with mass m is u, and under the influence of force F after time t, its velocity becomes v. Initial momentum of the object pi is equal to mu. U is for initial velocity. Final momentum of the object is pf, that is m into final velocity. Therefore, change in momentum in time t, that is delta p. Delta symbol is used in physics to indicate the change in the magnitude of a physical quantity. So delta p equal to pf minus pa, that is mv minus mu. As per Newton's second law of motion, F is proportional to delta p upon t. Substituting the magnitude of delta p, F is proportional to pf minus pi upon t. Now substituting pf minus pi as we have derived earlier, that is mv minus mu upon t, which gives m common in the numerator part. F is proportional to m into v minus u upon t. In the next step, you get F is proportional to m into a, because v minus u upon t is equal to a. In order to remove the proportionality sign, we multiply it with a non-zero constant. So F is equal to kma. K is a non-zero constant. Now take k equal to 1. So we get F is equal to ma. That implies force is the product of mass into acceleration. That is F equal to ma. Its unit is Newton or kg meter per second square. Moving on further in our video to the next topic, that is the usage of Newton's second law of motion in our day-to-day life. We see the cricketers, while catching a ball which comes from a particular height, they try to increase the time to catch the ball instead of jumping in the air. By increasing the time, what happens? The velocity of the ball which is coming towards the cricketer decreases. So the chances of injury to the cricketer is less. Whereas in case of a karate performer, he tries to minimize the time and he tries to hit the particular tiles with a greater force, which breaks the tiles into pieces. Moving on to the next topic, third law of motion. The statement suggests during the interaction between two bodies A and B, force exerted on body B by body A, which is denoted as FAB, is equal in magnitude to the force exerted on body A by body B, that is denoted as FBA, but it is in opposite direction. Let us see few practical examples of Newton's third law of motion. First example is when we jump from a boat to the seashore side, we are able to see when you jump from the boat moves towards the opposite direction. When we throw a ball towards the wall with some force, it comes towards us with the same force. When a gun is loaded with a bullet and when we strike it, it moves with a greater velocity towards the target, but the gun is pushed backward, which is also an example of Newton's third law of motion. So in simple words, the statement of Newton's third law of motion is action and reaction are equal in magnitude but in opposite direction. Moving on to the numericals. Before starting the numericals, as we had done in motion chapter, we make 5 columns: serial number, quantity, symbol, formula, and units. First quantity is force, which is symbolized by capital F. Its formula is F equal to ma and F equal to delta P upon T. The unit is Newton, kg meter per second square. gram centimeter per second square. The second quantity is mass. It is denoted by small m. M is equal to F upon A. The unit is kg and gram. The third quantity is acceleration, which is symbolized by small a. The formula is A equal to F upon m, or A equal to V minus U upon T. Its unit is meter per second square and centimeter per second square. Now moving on to the numericals of the ninth chapter. Hope all might have received the textbooks. Example number 1 suggests a constant force acts on an object of mass 5 kg. So mass is given 5 kg for a duration of 2 seconds. Time is given 2 seconds. It increases the object's velocity from 3 meter per second to 7 meter per second. So here you can see there is an increase in velocity of a body. So the least magnitude of velocity becomes your initial velocity, whereas the larger magnitude becomes final velocity. You are asked find the magnitude of the applied force. So you need to find force. Now, if the force was applied for a duration of 5 seconds, what would be the final velocity of the object? Now, first of all, as you all know, in order to find force, we should know the magnitude of mass and acceleration. If you see the given contents, you are given mass 5 kg, you are given initial velocity 3 meter per second, final velocity 7 meter per second, time 2 seconds. So from this magnitude, you can find acceleration by the formula V minus U upon T. That is 7 minus 3 upon 2, which is 4 upon 2, 2 meter per second square. So force will be mass into acceleration. That is F5 into 2, that is 10 Newton. Now, if this 10 Newton force is applied for 5 seconds, what will be the final velocity? So we'll just make use of the first formula of uniformly accelerated motion, V equal to U plus AT, where V we require to find U is 3 plus A is 2, which we have obtained, and T is 5. So 3 plus 10, which is 13 meter per second. Or you can derive from the formula of this chapter, V equal to U plus Ft upon M. Now moving on to the second example, which would require a greater force. A body having mass 2 kg to be accelerated by 5 meter per second square, or body B of mass 4 kg to be accelerated at 2 meter per second square. So we'll name it as body A, M1 equal to 2 kg, A1 equal to 5 meter per second square. Body B, M2 equal to 4 kg, A2 equal to 2 meter per second square. Now finding the force for both the bodies, we find F1 equal to M1 into A1. That is 2 into 5, 10 Newton. Whereas F2 equal to M2 into A2. That is 4 into 2, 8 Newton. From the magnitude itself, you can see that F1 is greater than F2. So body A having a mass of 2 kg is to be accelerated, or accelerating a body of 2 kg mass at 5 meter per second square requires greater force, that is body A. Moving on further to the third numerical, which suggests a motor car is moving with a velocity of 108 km per hour, and it takes 4 seconds to stop after the brakes are applied. So from the initial part of the question, you can see the initial velocity of the vehicle is 108 km per hour. It comes to a stop. Stop means final velocity is equal to 0 by the time of 4 seconds. You are asked calculate the force exerted by the brakes on the motor car if the mass along with the passenger is 100 kg. So we'll write down the quantities which are given to us. Initial velocity is 108 km per hour. We need to convert it into meter per second. So multiply it by 5 by 18. 18 ones are 18 six are. So 5 6 are 30 meter per second. Whereas final velocity is 0 meter per second because the vehicle comes to a stop. The mass of the car along with the passenger is given 1000 kg. The time at which the vehicle comes to a stop after applying the brake is 4 seconds. So acceleration is v minus u upon t, that is 0 minus 30 upon 4, that is minus 30 upon 4. If you reduce it, it is minus 15 upon 2 meter per second square. Now if you substitute it in the formula F equal to ma, where mass of the motor car along with the passenger is given 1000 multiplied by acceleration minus 15 upon 2, 2 ones are 2 500s are. 500 into negative 15 gives you negative 7500 Newton or negative 7500 kg meter per second square. Here negative sign indicates it is retardation. That means brakes are applied in the direction opposite to motion. I will give you a few time to just jot down the numerical solution. First example, one more time, u is given, v is given, t is given, and mass is given. So first of all, we can find acceleration by the formula v minus u upon t. Then substituting the magnitude of acceleration in the formula F along with the mass, we get the force applied on the body. Now, if this force is applied on a body for 5 seconds, you are asked its final velocity, which can be calculated by the formula V is equal to U plus AT. The second example, you are given two different bodies of different mass and acceleration. You are asked which body requires more force to get accelerated. Finding out the force applied on both the bodies F1 and F2, we are able to see that the body F1 is requiring more force to get accelerated. In the third example, you are given a vehicle is moving with 108 km per hour velocity. It comes to a stop after applying brake within 4 seconds. The mass of the vehicle along with the passenger is given to us. So in order to find force, we require to find acceleration. So acceleration, as we find it out, it gets reduced to minus 15 by 2 meter per second square. Substituting it into the formula F is equal to ma, we get negative 7500 Newton or negative 7500 kg meter per second square. Here, negative sign indicates it is retardation. Brakes are applied in the direction opposite to motion.